Hi everyone, welcome back. Today we're going to be talking about center of mass. You may have had some toys as a kid or seen videos online that use the concept of center of mass to have fun or kind of defy expectations. On the left there, you can see two forks balancing on a cup with just a coin. You may have seen that with a toothpick. And it's also fairly common to have toys, again, that utilize the center of mass, like this bird that can balance on its beak. So the center of mass is where something can be balanced, where if you leave it alone and it's resting on a single point, something can balance on top of it. So you may have seen something like this on a pizza box where it tells you where to put your hands if you only have one, or if you want to hold both of them together, because it knows where the center of mass of the pizza box with the pizza is, so it can help you balance it. So we can also use this for more complex systems, like this series of balls on the left. And all of these things are balanced on the center of mass here, right on that single point. And it doesn't have to be exactly at the center of mass because it's in 3 dimensions, but a vertical line that we can draw through the center of mass, anything will balance on, from your phone, if I could actually do it with a finger, to a book, to anything like that. So again, we can balance anything, and for a normal object, like these over here and not like this, the center of mass will be at the geometric center. It's at the center of its geometry, even if there's no mass, like a safety buoy or a donut or a bagel, anything like that. So the question is, why do we care? Well, we care because when something moves, it moves as if all of its mass was concentrated at the center of mass. So we can treat objects like a point, like a circle or a point particle in free body diagrams. And as an example of that, we have this video here where we throw several objects and they're spinning, and it's really hard to see what the path looks like. But if we turn off the light and we paint the center of mass with some UV light and we throw them again, it looks like our point is moving in a perfect parabola, because it is. These objects are moving as if all of their mass was condensed into the center of mass. So sure, this object is still rotating, but if we ignore that rotation and we look just at the center of mass, it moves normally there. So now it won't let me go do that. So this is important in an example like this. You don't know how to solve this yet. That's okay. This is something you're going to see soon. If we have a 4-person team pushing a sled on a frictionless track with an acceleration, and each person is applying a force at an angle, we want to know the magnitude of the force applied by each person individually and the normal force. So our steps to solve this would be draw a free body diagram, choose a coordinate system, and all of that. So before, when we draw a free body diagram, we draw an object, and then we draw all of the forces acting on that object from where they act. So we have an acceleration going to the right, our gravitational force acting downward from the center of mass, normal force acting upwards from the surface, and the force of our team pushing downwards at an angle. But when we look at this, there's arrows all over the place. They're starting in different places, pointing in different directions. There has to be an easier way, and there is. Since objects will move and act as if all of their mass is at the center of mass, we draw the center of mass. We draw the point particle, and then we just draw all of the arrows pointing away. So we still have our gravitational force going down, our normal force going up, and the force of our team pushing. But this puts the beginning of all of the arrows in the same point, and it makes it easier to break them up into x and y components and solve. So we're still trying to find the magnitude of the force applied by each team member and the normal force. Well, now it's much easier to go and split the force of the team up into its x and y components and apply Newton's second law.